Nice meeting you, everyone. So today I will present you our framework for privacy-friendly AI. So I guess you see my screen. Just little disclaimer. You might have seen BastionAI, but we extended BastionAI to cover more things, as I will discuss. It's now called Bastion Lab, but okay, just little note. So today I will talk about how to make it easier to train AI models on confidential data, especially in multi-party setups. You might know this case, which is actually called federated learning. But as a reminder, the challenge is how can I help train an AI model on several parties dataset? Because having a diverse set of data helps have a model that is more accurate, less false positive, less false negatives, and generalize better, which can be critical in some applications such as healthcare for cancer diagnosis, for instance. But the issue is, how can you help those data owners collaborate without risking the privacy of each hospitals? One method you might know of is called federated learning, which is quite popular today. That's been democratized by Google. And the idea is that, okay, because data is a bit sensitive, we might not move it directly, but we're going to move the gradients to train the model. So we have a data scientist who designs the model, send it to an aggregator. The aggregator dispatches the model to each hospital. Then the hospital, using their local compute and machines, train their model locally, get their gradients, and then send the gradients back to the aggregator. And then the aggregator will aggregate the gradients, get a new model, redispatch it, and we work like this in a loop. So it looks that it's working, but there are a lot of issues actually. The first one is deployment, because you might have seen that each hospital must perform the computation themselves, and therefore each participant needs to have the hardware and software stack to run the computation, which can be quite difficult if you imagine that we train, like for instance, some GPT-3 models that require huge GPUs. You might not think that every hospital that is participating has this, and even in terms of deployment and maintenance, you need to always update everyone, which can be quite difficult. Then there is an issue of communication, because as we move the gradients at each iteration, it is quite expensive. And again, if you have large models, that means large gradients and therefore a huge communication bottleneck. And finally, even though the data is not set in clear, gradients can be, and in most frameworks, gradients are set in clear, which can pose a privacy issue because you can reverse engineer more or less easily the data from the gradients. And also, you don't know if each participant put the right data in the model, and you have no integrity of data and computation in this framework. And for all these reasons, federated learning sees still a lot of challenges, deployment communication being the biggest obstacles for an easy deployment. So to answer this issue, we'll propose a new framework, but to understand how it works, we need first to understand what is confidential computing, which is a key technological component of our solution. So for those of you who might not be aware of confidential computing, it's the use of hardware-based trusted execution environments to secure data while it is being used by someone else. The idea is that some processors that you might find today from Intel, AMD, or NVIDIA have the ability to create a secure environment so that your data can be handled by someone else remotely without them seeing your data. As we'll see, one of the first major property is what we call data in use protection, so that someone else, not in your infrastructure, remotely, in an infrastructure you do not master, can compute things on your data without them seeing it, thanks to some end-to-end encryption mechanism. The second key feature is what we call code attestation, which provides cryptographic proof that only a code you know and trust is executed on your data, and therefore you can have integrity of data and computation. What does it mean that data is protected during analysis? The idea is that whenever we have sensitive data to have to have someone to handle it remotely. For instance, in that case, train an AI models on your data remotely. Then we will do this in a secure enclave, which is a kind of black box environment where there is hardware protection, whether it is isolation or encryption of memory, so that even if I am a cloud, an AI startup in, let's say, AWS, and I want to train an AI model on your data that you send me, and when I say you, I can, let's say, a hospital. Well, if that data is being handled inside an enclave, even me as an administrator of the VM or AWS will not be able to see the data that is being manipulated by our machines, even though we somehow manage it, because there is this kind of hardware protection mechanism. That is that, okay, that's great. Let's suppose I want you to manipulate my data, and I know that because you're using secure enclave, you will not see it in clear because it's only accessible in this secure environment that you cannot compromise. But then the question is, how can I know that even if you use a secure enclave, that you actually have one? Because maybe you are not using one, so there is no guarantee. Or maybe you put a malicious code that is leaking the data outside of the secure parameter. And that's why there is a mechanism called code integrity, with remote attestation. And the idea is that before the client, let's say the hospital, sends data for someone else to train a model on it, the idea is that they will perform what we call attestation. And those hardware are specific CPU instructions to generate a kind of identity of the enclave, of the code that will manipulate the sensitive data. And it could contain information about, let's say, I don't know, like what firmware we are using, a lot of security parameters. But the most interesting one is that we generate a hash of the code of the enclave, and we'll have it signed by a key that is only available to the hardware. Each CPU or GPU with that secure enclave ability have tamper-proof hardware that are written on the hardware, so that they can sign it with a key that is not accessible by the guy who might manipulate the enclave. Because, as I mentioned, those keys are tamper-proof from the outside. And therefore, that means that once I've generated my identity of the enclave and I've signed it with the key of the enclave, I cannot forge it. I cannot forge another report that says, look, I am an enclave, because I don't have the hardware key. But of course, to have to understand, to make sure it is indeed one enclave, you will then send that report to the hardware provider, let's say, for instance, Intel, and they have the list of the keys that are embedded on the CPUs they sold, and they can verify that, oh, okay, you're showing me some kind of identity of an enclave, and it's signed by a key that indeed comes from one of my CPUs. And then it says, okay, I will attest that this is indeed a genuine secure enclave report, and I will send it back to the user. And then the user will check that, for instance, Intel has indeed signed it. Intel, in that case, will be the root of trust. And then we say, okay, if it is indeed what it says, I know that actually I'm talking to a secure enclave with the right security properties. Especially, I know that there is a specific hash of a code that is loaded inside the enclave. And therefore, if the code is open source, I can reconstruct the hash and compare the hash that I am expecting with the cache I observed. And if those hashes don't match, that means that there is some malicious code, or at least there is not the right code behind. So I've been talking a lot. It's a lot of stuff to handle. So I guess it's good to have a little demo to see how it works in practice. So you can go to this space from Hugging Face, where we'll see how it works with a concrete example. I will let you have a look, or maybe I can put that in the chat afterwards. I will just wait 10 seconds. I guess I can put that in the chat. Okay. So here it is, and let me show you how it looks like. Let me share you the screen. Okay. So this is an example on Hugging Face. And the idea is that we'll see what it means to use a secure enclave. So to use the secure enclave, it's a bit like going from HTTP to HTTPS in the sense that, okay, I've put 3 servers behind. 1 server without enclave. And because there is no secure enclave ability, I have no guarantees that my data will be protected, that it will remain end-to-end encrypted. But because there is no attestation linked to this, I can detect that. Even before I send data, I can detect it as much as, when you're using, I don't know, HTTP, when your browser goes on a non-HTTPS website, you can detect it. Well, this is the same thing. There is some security check that is failing. And even if, okay, taking a lot of time to react. Maybe I will start it. Okay. Okay, I guess this is a demo effect. Okay, let's try directly. Is it okay? Okay, little issue. Okay, so I guess I will show it. I have an example. I have another recording, so I will send it. But yeah, you can imagine that it detects the error, and then once it works, I mean, the idea is that if there is a malicious code, we'll detect it because we'll observe that there is the wrong hash, and if there is a right hash, we can then use our AI models as usual. Okay, I will go back to the rest of the presentation. So sorry for this little issue. We have recordings of times where it worked. I guess I should not have been so audacious, and there is a demo effect. But let me show you. I don't know if you see my screen correctly. Okay, no, this one. It's not a full screen. Sorry. Okay, let's get back to it. So now that we've talked about confidential computing very quickly, we saw that confidential computing can allow you to have someone else analyze your data without them seeing it, because it remains end-to-end encrypted through those hardware technologies. And the idea is that instead of using a federated approach, we'll have a centralized approach that will be much faster and easier to perform, but that will be protected by secure enclaves, and therefore we have the privacy guarantees. So that's what we call fortified learning. And the idea is it will be much simpler. The AI provider uploads the model inside the secure enclave. The hospitals upload the dataset inside of this, and then we train everything locally inside this single enclave or this cluster of enclaves. And the idea is that with this scenario, all the infrastructure effort can be centralized in a single node. You don't need anymore to have each hospital have the CPU and GPUs needed and the software to perform computation, because computation is externalized to the single node, thus making it much easier. And actually, the only thing you need to have on the hospital infrastructure is just the Python package to remotely attest that you're talking to secure enclave. But this is very lightweight. You can imagine running that on a laptop. And therefore, the hospitals could send their model simply from a web browser on a simple laptop and externalize also computation externally. And therefore, it is much easier for them to be onboarded. And you can manage everything. Therefore, you don't need also to update your software on each node, because the update can be concentrated inside the central point. Also, in terms of communication, we communicate much less because everything happens inside a single cluster. There is no need to go back and forth between a node and the central the aggregator, which make it much easier, especially if you train large models. In terms of security and privacy, because we're using secure enclaves, data, the model and the data and the updates are hidden from anyone else thanks to end-to-end protection. And we have can have integrity check, as I mentioned, for attestation, and therefore we have integrity of data and computation. Just going a bit fast. And so how does it work in practice? So the data owner comes, upload the dataset inside the enclave, then the data scientist remotely interact with it. They never have the data locally. They send computational plans, for instance, train such deep learning models. And once it's done, they can fetch the results. So we have one concrete example where we fine-tune the transformers on a private dataset with differential privacy using our framework. Let me share the screen. Okay, so you can find it on Bastion Lab. This is our GitHub. So as I mentioned, Bastion Lab is, I can come back to this, but Bastion Lab not only covers deep learning training, it also covers data exploration and other things. And we are starting to merge it, BastionAI, into Bastion Lab to make it to have a unified framework for both. So here I will show you historically when I wrote the proposal for PyData, it was for BastionAI, but now it's being merged. But you can still find the old BastionAI repository inside. But within 1 or 2 weeks, you will have a clearer and unified framework. So the idea, as I mentioned, is to show how we can train an AI model in this fortified learning framework. The idea is that we provide a Docker image that you deploy on your secure hardware, and such hardware can be found on GCP or Azure, for instance. Then the data owner gets their dataset. For instance, we took a dataset for spam classification. They do the pre-processing first in an offline phase. So data scientists prepare the model, for instance, a distal bed for classification here in an offline phase as well. And when they want to start training, they go in a more online phase. So the data owner first connects to secure enclave and performs attestation. If there is any kind of error, for instance, the secure enclave, there is no proof that this is a secure enclave, or the code, the hash of the code is not the right one, an error will be raised, and it will not continue any further. But if it works, we can upload a dataset remotely, for instance, the SMS spam classification. We can also define a privacy budget. Okay, here it's 1 million, but it's not very realistic, but you can put whatever you want. And the data scientist then connects to the secure enclave remotely, and you can get a list of the remote datasets. These objects are just metadata that he has locally that have information about the remote dataset. And he will use that, for instance, to create what we call a remote learner. This is a bit similar to FastAI learners objects, where you provide a model and a dataset, but here we provide a remote dataset. So all this happens inside the data scientist infrastructure, and therefore it does not have access to the dataset directly, but only as a pointer to that. Then the data scientist can provide other parameters, for instance, the loss, the optimizer, and so on. And then you can call a fit function. The fit method will simply send to the remote enclave the instruction to begin training the model that the data scientist uploaded on the remote dataset, and with differential privacy. And when it's done, when training is done, then we can pull the model and get the model locally using a get model method. Here it is a single dataset scenarios, but covering the multiple dataset scenario is not hard. where we'll just have several data sets that have been prepared that are merged, stacked inside the enclave, and then the data scientist will, in the same manner, just trigger a training on the whole data set. So let me go back to my slides. Da, 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 da. Yes. Now we can see some benchmarks of the performance of our approach on the fine-tuning of an efficient net model, therefore for computer vision. And so this is done on an AMD EPIC CPU. So AMD has the ability to create those confidential VMs that provide, as I mentioned, the data in use protection. And that's why we did the first benchmark on this. And you can see there are several frameworks that are being tested. We are using PyTorch without any privacy mechanism as a baseline. Then with PyTorch with Opacus. Opacus is a PyTorch library for differential privacy, which, as you see, greatly increases the training time. The bigger, the worse it is, because it's amount of time it takes to do one epoch. Then you have PyTorch with 2 nodes, which is therefore in a federated manner. And then you have PyTorch with 2 nodes with differential privacy, which is the slowest one, but with the highest level of privacy in a federated approach. You can see that BastionAI with differential privacy is actually quite competitive because it is 10 times faster than PyTorch with differential privacy in a multi-party setup. We also have similar results on GPUs, even though it's less, the difference is not that big. Well, you can see that PyTorch in a federated approach with differential privacy is 3 times slower than BastionAI with differential privacy. And so regarding confidential computing, as I mentioned, this is something that is getting hot. And you might think, okay, you're talking about hardware, but what if I don't have the right CPU or GPUs that have those abilities? Well, good thing. Most cloud providers now have a confidential computing offer, as you can see. Azure being one of the most leading solution with both AMD, so NVIDIA, and Intel secure enclaves. Yeah. And as I mentioned, as you can see on the bottom, yes, Intel has been the first one, but AMD followed quite quickly. And the interesting and good news is NVIDIA will provide in their next Hopper GPU confidential computing abilities, which was not necessarily the case before. And therefore, this opens a lot of opportunities because before we could only use CPUs. But now you can imagine having a cluster of NVIDIA GPUs to train AI models on confidential data, financial, healthcare, biometrics, and so on, without risking privacy. So if you're interested, I will be very happy to talk with you. We have a Discord that we have recently kickstarted that you can join. I can share the link. And there is also, we have 2 repositories. One to deploy AI model, which is called Blind AI, and one called Bastion Lab that covers training and also data exploration and visualization. So I don't know if there are any questions, but I'll be happy to answer those.